Let us learn the electrical properties of colloid. Actually, almost all the colloids are categorized either as positive colloids or as negative colloids. Or the classification is based on the charge of the dispersed phase. That is, if a colloid is categorized as positive colloid, then the dispersed phase in that colloid is positively charged. Same way, if a colloid is negatively charged, then the dispersed phase, the colloidal particles in that colloid are negatively charged. So, if we consider a colloid, imagine it is a positive colloid, then the colloidal particles are positively charged. Existence of all the same charges together is not possible. So, to balance this, the medium of this colloid will be oppositively charged. So, oppositively charged. That means equal amount of dispersed medium will be here having opposite charges. That is, here all the colloidal particles are positively charged, so the medium will be negatively charged. Okay, anyway, here I am going to write some examples of positive and negative colloids. Examples of positive colloids are ferric hydroxide, FeOH, thrice colloid, and aluminium hydroxide colloid, aluminium hydroxide, and metallic colloids like salts of lead, bismuth, iron, etc. are positive colloids. Indicators like methyl, violet, methylene blue, etc. are some examples of positive colloids. And negative colloids, examples of negative colloids are arsenious sulfide, As2S3, arsenious sulfide, then cadmium sulfide, CdS, and antimonic sulfide. The metals like salts of silver, gold, platinum, etc. are also negative colloids. And silicic acid, tannic acid, etc. are also categorized as negatively charged colloids. What are the reasons behind the positive and negative charges of colloids? Okay, move on to that. Three major reasons behind the charge of colloidal particle or behind the charge of a colloid are, the first one is preferential adsorption. Preferential and the second reason is dissociation of the surface molecules. And the third reason is the presence of acidic or basic groups. Presence of acidic or basic groups. Okay, let's discuss these things in detail. The first one is preferential adsorption. The colloidal particles usually show some tendency to attract some specific type of particles or we can say shows some preferential attraction towards some charged particles. That is, the colloidal particles shows affinity towards either with positive charges or it may shows affinity towards negative charges. That depends upon the colloidal particles. For example, if we prepare ferric hydroxide salt, FeOH thrice salt, so the colloidal particles are FeOH thrice. Actually, this salt, this ferric hydroxide colloid is prepared from ferric chloride. And the hydrolysis of this ferric chloride leads to the formation of the salt ferric hydroxide. So even after the formation of the ferric hydroxide colloid, trace amount of ferric chloride will be in the medium. So what happens is this Fe3 plus ions in the ferric chloride, Fe3 plus ions present in the medium will be adsorbed over our colloidal particle. Because ferric hydroxide shows affinity towards positively charged ions, and the positively charged ions present in this medium is Fe3 plus, that is from the trace amount of ferric chloride present in the medium. So that is why, due to this preferential adsorption, the ferric hydroxide salt is categorized as positive colloid. Okay, what about arsenic sulfide? Here, arsenic sulfide As2S3 is prepared from hydrogen sulfide H2S. The ions present there are H plus ions and S2 minus ion. H plus and S2 minus ions are there in the medium. So what happens? This As2S3 shows either it can adsorb this one or this one. But the preferential adsorption of As2S3 particles is towards S2 minus ions. So S2 minus ions will preferentially adsorbed over these colloidal particles. And it acts as a negative colloid. That is why arsenic sulfide is categorized as negative colloid. In some cases, it is possible that the colloidal particle, the same colloidal particle can, if it is A, this same colloidal particle can adsorb both positive and negative colloids. The adsorption of positive and negative colloids are not at the same time, but in some situation this particle can adsorb positive, and in some certain cases this will adsorb negative colloids. So that preferential adsorption will be based on the amount of the charges present in it. The colloid silver chloride is coming under this category. Actually, silver chloride colloid is prepared by the reaction of NaCl, sodium chloride, and AgNO3, silver nitrate. Silver chloride colloid is prepared when sodium chloride is reacted with the silver nitrate. So assume that we are adding excess of silver nitrate into sodium chloride. Actually, if we react sodium chloride and silver nitrate, the ions present in the medium will be Na plus, Ag plus, Cl minus and NO3 minus. These are the ions present in the medium. So, if we add excess of silver nitrate, what happens? Or what are the ions present excess in this medium? One is Ag plus and the second one is NO3 minus. When the colloid formed, AgCl is there, AgCl is there, AgCl particle, AgCl colloidal particle will be formed. In addition to that, excess of Ag plus and NO3 ions are there. And this AgCl colloidal particle will preferentially absorb Ag plus. It shows more attraction towards Ag plus. So, a layer of Ag plus ions will be formed over AgCl particle. So, it acts like a positive colloid. Act like a positive colloid. On the other hand, imagine that we are adding excess of NaCl to silver nitrate solution. So, what are the ions present here in excess? One is Na plus ion and the next one is Cl minus ions. So, when the colloid is formed, AgCl colloidal particles are there. In addition to that, Na plus and Cl minus ions also present in trace amount. So, among Na plus and Cl minus ions, silver chloride particle shows more attraction towards Cl minus ions. So, Cl ion, a layer of Cl minus ion will be formed over the colloidal particle. So, in here, the colloid will be act as a negative colloid. That means there are some colloids which can act both as positive colloids and as negative colloids. So, we can rewrite this equation as NaCl plus excess AgNO3, AgCl salt, and the AgCl is positive colloid. So, if excess NaCl plus AgNO3, AgCl colloid having negative charge. Then the second reason, that is dissociation of surface molecule. This is common in soap. We know soap is the higher fatty acids of sodium or potassium. So let us take an example, that is sodium palmitate. Sodium palmitate. So, sodium palmitate is C15H31COO Na. So, usually what happens is associated like this, C15H31 and COO minus and Na plus. So, in soap, what happens here is the dissociated ions, negative ions, that is C15H31COO minus ions will be associated or will be aggregated over the surface of the colloidal particle. So, the dissociated ion from the colloidal particle itself associated over the surface, and that leads to the formation of charged particles. Then the third reason is presence of acidic or basic group. This is common in the case of proteins, amino acids, and polypeptides. The basic structure of an amino acid is NH2, H, COOH, and R group. Different amino acids are there based on the difference in the R group present here. Anyway, all the amino acids contain these three groups in their basic structure. Actually, the amino acid containing a basic group and an acidic group. In addition to that, the R group can be contain an acidic functional group or basic functional group, etc. Okay, let us learn how these amino acids behave in acid and basic medium. So this is NH2, COOH, H and R. At a particular pH, there is no negative or positive charge in this molecule. We can draw this structure as like this also, NH3 plus, COO minus, H, R. So the pH at which this molecule exists like this, the pH at which the molecule exists as uncharged particle is known as isoelectric point. Isoelectric point. Isoelectric point is the pH at which the amino acid molecule or the colloidal molecule exists in uncharged state. So when pH decreases, pH lowered means it is acidic medium. It is acidic. The medium is acidic. So in acidic medium, what happens is this basic group will be protonated. That is NH3 plus. This group converts to NH3 plus. The acidic medium provide one H plus to the basic group. And this converts to NH3 plus. That is charged. A charged molecule will be formed. Same way, when pH increases, that is in basic medium, what happens is this group will be deprotonated. So this will be converted into COO minus. Here also the molecule is in charged state. So basic medium deprotonation occurs and the acidic medium protonation occurs. Anyway, the molecule exists in charged state. Only in a certain pH only this exists as uncharged particle or uncharged state, and that point, that pH is known as isoelectric point. Now we are going to learn electrical double layer formation. Double layer formation. That is how the preferential adsorption occurs over the colloidal particle. The ions which are adsorbed over the surface of the colloidal particles are known as potential determining ions. They are known as potential determining ions. The nature of the charged particles adsorbed over the colloidal particles was first described by Helmholtz. And later it was modified by Stern. So, Helmholtz double layer formation. To make it clear, consider a colloidal particle which is preferentially adsorbed by positively charged particles. So, according to Helmholtz, colloidal particle will adsorb either positive or negative charge. Here, the colloidal particle is preferentially adsorbed positively charged ions. So, a layer of positively charged ions will be formed over the colloidal particle. And the layer formed over the first layer formed over the colloidal particle is fixed. Since the first layer is positively charged, a layer of negatively charged particle will be formed over this first layer. And the second layer formed here is movable. So the first layer is a fixed layer and the second layer is movable. And the ions in the second layer is known as counter ions. Counter ions. The ions in the first layer is potential determining ions. This is potential determining ions. So the combination of the fixed layer and the movable layer is known as Helmholtz double layer. Later this model was modified and the modified model is known as Stern double layer. So in Stern double layer, the concept is modified as the colloidal particle is preferentially adsorbed by ions, and it is composed of both positive and negative ions. And this layer is a fixed layer and it is called as compact layer. This is compact layer. Then the next layer is composed of counter ions, and here the counter ions are negative ions, but the counter ions are diffused in positive medium. So here also negative and positive ions are there. Negative ions are diffused in positive medium. And this medium is known as, the second layer is known as diffused layer. Diffused layer. The first layer is a fixed layer and the second layer is a movable layer. And the combination of these two layers, combination of compact layer and a diffused layer, is known as Stern double layer. When we apply electric field over colloidal particles, when we apply electric field over a colloidal particle, what happens is this diffused layer move opposite to that of the electric field. So what happens is an electrical potential difference, a potential difference will be developed between the compact layer and the bulk of the solution across the diffused layer. So when we apply electric field, the diffused layer, diffused ions are move opposite to that of the electric field, and an electrical potential difference will be created between the compact layer and the bulk of the solution across the diffused layer. And that potential difference developed here is known as zeta potential. Zeta potential. Or we can call it as electrokinetic potential. Zeta potential or electrokinetic potential is the potential difference developed between the compact layer and the bulk of the solution across the diffused layer.